Okay, number 3 video. And I said I'm just going to stack this up to get to where we need to go. Identifying marks now roughly where we see where the bridge breaks during the video collapse. And here. That would put the span, this span, or it's right past the nodal area. Let me make that clear. So the stresses, the flexural moment is experienced right past the nodal area. So it might be a little closer there. Now I added this bar in here. This is going to represent our steel bar. A B bar. I call it the B bar, the upper bar. Now there's a lower bar in here that's tied to the deck. This number 11 will double as our bar. And it will, so this will double as our bar and indicating of number 11's location. Relationship to 12. Remember there's a chamfer here. So I'm going to have some separation. Now I will put back some more details for you guys that still have visualization issues. There's one engineer that keeps writing me on the side there that he's quite stuck in the past. So he doesn't understand how bridges work, how the truss systems work. I'll show you links on it. So LT or LTJ or whatever heck your name is, you need to get a little brain, a little knowledge in you. You said you're retired. You're a retired engineer. I don't know what engineering you did, but maybe you should just stick with whatever that was, and don't strain your brain on something you can't conceive. All right, that's my tack on that. So look, this is the connection here. We know that I can't pull this out anymore without pulling that, right? So if I pull that, it pulls that. If I take this away and pull that, it will flex this, creating a moment here. So if I were to loosen this, and it's loosened at the top, as I loosen it, it will widen depending on the forces. So here now, so now they loosen, detensioned, and the load of the deck still going downwards creates that split we see. We see a split in the base of number 11. Well, that's the reaction there. When they detension more, it allowed this to kick out more, the bottom to kick out and elevate. Well, this flexes up, remember? This can flex up to that degree. I mean, it can flex even more than that, but now you see the flex in it? That would create that tension break inside here, the way the concrete split at the bottom of 11. It also did a torque, a rotation. That's why I have this off center also, this column off center to remind me of that. Your post-tension bar then regrips, so it can't go any further. It stops. What's holding it now is, of course, part of its diaphragm here, and the bar inside the concrete. They go to retention. This is all split and cracked. They go to retention. They're doing it from the other end, but I'm going to take a little liberty and do it from this end. And it starts pulling it in. And it pulls it in where they go to work on the A bar. As they pull it in, this is crushed up material back here. This concrete is defective, it's broken. Dirty hands now, right? It's broken, and the forces are still on it. It eventually blasts through that column where the forces smash, or should I say shatter, the base of the column. That now removes this interlock all the way from that point, mostly because the forces are not only being applied from here, by trying to clamp this back into here, this is already deflected, I think. Let me show you an exaggeration of that deflection. See it? By trying to clamp it back in, I'm going to lift it now. They're trying to pull the base of this like that. I'm creating a torque action there, right? So they're trying, I'm actually up here and there's reaction down here. So they're trying to do that. But you can't put the cat back in the bag for this weight of this bridge and this structure. It can't lift up the mid-span. Now, if this thing really worked, the bridge deck worked, it wouldn't have deflection. The moment you get deflection, you're no longer at a compressive design. And that deflection, let's add a weight to it, that deflection is exaggerated like this. Although they never gave us any measurement, there's your deflection. And as you can see, that's the deflection. It's experienced the moment right here. Right beyond this nodal area here is where it identifies itself. Everything else looks so-so, but right here is where you can see. Now I'll take the weight off. Let's see how much of a rebound it has. Well, this is metal. It's not going to want to rebound too much, but we're back up here. Now they shimmed the bottom of this, so shimming it when they were post-tensioning also creates, to close up that gap, also created some drag and some drama going on there. Gave probably a false illusion of the torque numbers, I would think, now that it's shimmed. I don't know. Let's move on. Let's go ahead and do the next video, but this should get you to this step. Remember, sagging took place, reported by the FIG engineer, and stated that it's nothing. Sagging, of course, can't happen in this structure, because if it's sagging, these members are no longer in compression. If they're sagging, you're putting a torque action or a rotation out. You're creating a hinge point out here beyond that nodal area here, and off of the other one also. Detensioning this again, release the base of this to allow this to even go down more and create more of, sag more and create more of that. Let me terminate this video and I'll give you more in the next video.